So what did we learn yesterday? We learned that if we take the focusing heat equation, like this, if we normalize the flow using the one parameter, so it's a dynamical rescaling, so you use, so maybe this is a V, this is a tau and Y, so you zoom on what maybe you expect to be singularity, and ds d tau 1 over lambda squared, and I choose the self-similar law. So this is lambda t square root of 1. Okay, then what happens is that when you do this, you map your flow onto another flow, which is d tau v is Laplace v plus v minus a half. It's plus or minus 11, so it's 2 over 3 minus 5v. Let's write that by v. And then we have a complete understanding of what kind of solutions of this equation you should expect. There are 3 possibilities which have been studied in the literature, and sometimes people can even tell you that these are classification theorem. There are 3 kinds of solutions that are known, and that corresponds to block regime with this equation. So regime 1 is what I call the front. It means that to leading order, you look like a constant. This is the front solution. Second possibility, you are just a self-similar solution. In some sense, this is and you decay at infinity. So this is what people like to call type 1. And the third possibility is that you are type 2. Type 2 can be understood by saying that in some sense, this is not, you did not renormalize with the right window. There is another window to, in this picture, you still concentrate. Type 2 means that you're still having, even after renormalization, you're still concentrating, so this is so-called type 2. So these are really, it means that if you take your PD, you renormalize self-similarly, and you immediately see that there are, people worked a lot to see that there are 3 possible regimes. This type of front singularities, type 1 singularity is given by a self-similar solution, type 2 singularity is given by something more complicated, and the fact that there is another inner window. Okay, so this is for the heat equation. So now if you take a Schrodinger equation, and you go through exactly the same procedure, so you normalize and you say, all these regimes still make sense for a non-linear Schrödinger equation. And the answer is type 1 and type 2. You certainly expect that they make sense. So this is expected. This is the theorem. This is something we did with Hermann himself. In 2015. So you can certainly have some, for the focusing NLS, you certainly have this type of type 2 singularities, and actually front singularities, it's a little bit more complicated. They have been studied in a slightly different regime. So it's let me not talk about front in this page. Okay, so this would be for the focusing NLS. So now today I'm going to ask, well, what about the defocusing NLS? So let's start with the defocusing heat equation. So I said in my first lecture that if I take a defocusing problem, if it's the parabolic problem, there is no singularity formation anymore. It's a direct consequence of the maximal principle. It means that all this picture completely collapses. You could renormalize, try to look for a suitable solution. They just don't exist. Okay, this is automatic. So if you go to defocusing NLS, if you put an I here, what you expect is that again, the kind of, so this would be, I'm sorry, so it doesn't matter. So if I have the defocusing NLS, and if you try to implement this kind of renormalization and look for this kind of profile, again, you expect that this scenario do not exist. Well, I don't have theorems for you. We need to look into more details here. What's very easily seen is that the trivial front does not exist. Type 1 would typically mean that the solution does not break scaling, but it's been proven by Bourgain last year that a globe solution for defocusing needs to break scaling. So this guy is not well adapted. And type 2 really relies on the existence of solitons, and solitons in the defocusing case, this would correspond to this equation. So if you look at radial solutions that decay at infinity, it will seem that there will not be any such solution. Okay, so in some sense, the natural guys that you know in the focusing picture do not exist. However, what still is there is the strategy, because you see, there's a point here. In the focusing case, type 1 solution corresponds to an exact solution of the self-similar equation. Okay? But type 2 and front singularities, it's something more tricky. It corresponds to solutions that exist, but that are approximate solution of the flow, and that correspond to specific regimes. You see, typically type 2, it means that you're not looking at the solution at the right scale. You still have to renormalize. You just started your renormalization procedure. You don't see it at this level. Okay, so the idea was really for this problem, isn't it the case? So you start by renormalizing. So you start with, so you have your defocusing NLS plus the Q minus U2. You renormalize self-similarly exactly like for the heat equation. You hit something like, so you look for something that wants to concentrate. So you do exactly the same renormalization. You will get the self-similar equation. It's the same I theta plus Laplace d. You will have minus I 1 over 2, 2 over 2 minus 1 d. Let's write that plus d. But now you have minus d. P minus 1 equals 0. You want to find global solution of this equation that remain of size 1. None of your candidates wait, but what you need is you need to understand, so you need another renormalization. You need to understand that you're not looking at the picture, you're not looking at the right at the right picture. And this other normalization is very simple. It's a blend of front. That is, you need to change variable. You need to say that z is what we call square root of b times y. So b is a b of tau. I'll explain this in a minute. So I will look. So I'm changing space. I look for something that wants to invade the whole space, but it's also type 2. I will allow for growth. I'm going to have solutions that of this equation that actually grow. So explicitly, what you do is the following thing. So maybe what was a little bit mysterious in the beginning is that I'm not able to tell you what I do. V is not the right variable. To do this, I need to pass to the hydrodynamical variables, meaning that I do the following thing. I transform so my v of time y, which is supposed to be a solution of the self-similar equation, this thing over here, I transform it, so I change variable, I zoom again, so the transformation I wrote it here, so but we do it in phase and modulus. So it's 1 over square root of b to the 2 over p minus 1. It's some function rho, which is going to be the modulus of tau and b z, and then I allow for the phase psi and tau and z, and I divide by b of tau. Okay, so you should find that b, so b is a function of tau, and b is expressing the fact, so I have a front, I am spreading like this, b is the speed of the front. Okay, so I'm going to parameterize the speed by asking for b to be exponential of some minus eta. Okay, so e is a number which is strictly positive. I don't know how to choose this number so far. I will explain you how to choose it. So see, the point of this renormalization, I'm doing something in phase and modulus. It's not very clear what you're doing on the real and the imaginary part. And the reason why you do this transformation is that maps the flow. That's exactly the philosophy in particular behind type 2. This is exactly what's going on here. It maps the flow onto simplified. Something gets simplified, and I can tell you, so I'm going to write this equation once, but it's just to so if you do this transformation and you say exactly what you get, I can write the equation on the board. So I get exactly this, minus rho Laplace psi minus 1/2 L minus 1 over R rho. Then I have an operator twice dz plus 1 over R z dz rho. So this is the first equation. And the second equation is rho d tau psi is equal. So I'm going to put, I'm going to put this in red here. have, so this plus here, this is b squared Laplace rho. And I get something like minus grad psi squared plus 1 over r times r minus 2 psi. Okay, and then I have a bunch of terms, and I have plus 1 over mu, 1 over r psi, and this is the peak R basis here. And I have plus rho to the p minus 1, and the whole thing is multiplied by rho. Okay, whatever awful thing. This is a system, and there is nothing new in writing NLS in hydrodynamical variables. It's called Madloom transform. People have done that in various settings. Maybe the novelty here is to believe in this variable from A to Z and to really do the analysis. These variables show you something, this decoupling, that it is not easy to see if you stay with me. So what is my point here? My point is the following thing. What this transformation does, it creates this rectangle, b squared Laplace rho, but you have another Laplace here, which is this term over here. Okay, so in some sense, what I can pretend, so I can think that, so if I believe in the front, it means that I believe that my function b of tau is going to go to 0 asymptotically in tau. So I can hope that in the first approximation, my flow is governed by the flow without this term. Okay, this is so I'm looking for regimes where actually this is going to be the case. And you see the point is that in my equation, you see, when you have type 1, when you have the front for the heat equation, the solution is a constant, so it completely kills the Laplace term. Here, you don't kill the Laplace term, you just kill part of it. Okay, you kill the Laplace in the density, but Laplace is still here in a velocity. Okay, so now the strategy is very clear. If I am able, I want to construct global solution of this equation, which I understand well. And then I need to understand, then once I've understood them well, I need to be able to show that this term is going to be lower order in some sense, that it's not going to ruin this flow. Okay? And there is something that you know from scratch. You need structure. This term contains the highest number of derivatives in your equation. It has to push for you at some point, because otherwise you cannot put the highest number of derivatives of your equation on the right. Okay? So this term has a structure, it's going to push for you. So what is this equation? This equation is verbatim compressible Euler written in self-similar form. Okay, it's exactly this. Okay, so the equation, if I put the red term to be 0, or if I ignore the red term, so if I ignore the red term, if you want, this equation, so I need to shake it a little bit, but it's verbatim to you. Velocity would be the gradient of the phase. This thing is exactly compressible. Okay, so the problem becomes very simple. What you need to do is understand. So there are two things you need to do. You need to understand global solution of this equation, so global solution of compressible Euler. So this is after self-similar normalization, such that the red term is lower. So there is something I did not tell you. I did not tell you. So my space variable is z. I did not tell you what r is. So there's a parameter here, which is, so it's a number. So r is just 2 divided by 1 minus e. And what is e? Is the velocity of the front. Okay? So I'm looking, if you give me a positive e, it creates an r, and I want at the end of the day, I want this term to decay in space, so I want e to be positive. Okay, which means that I want e positive, so I want r strictly bigger than 2. But at this point, these numbers are given to me. I'm just doing this transformation. I have no reason to choose them, to choose this term in this or this way.
For those of us who don't know Euler well, what p correspond to in Euler?
Oh, yeah, so it would typically be gamma, right? It's exactly pressure. If you want, this is the Bernoulli formulation of the radially symmetrical. This is what you get, but this is what you get when you integrate on the Bernoulli. Okay. So okay, so this is so if this is Euler, then the first natural thing to do, this is exactly the point. This renormalization shows you a new equation. It simplifies the flow, and now you can ask yourself, but this new equation, does it have non-trivial solution? Okay, in particular, non-trivial stationary solution, which is the simplest possible regime you could be looking for. So what you're asking, at least reduce, just stay in radial symmetry, because there is no reason at this point to make things more complicated, and just ask yourself, what do I know about radially symmetric solutions of compressible plane? Self-similar solution of compressible plane. In other words, it is a stationary solution. You just remove time difference. Okay, this is a system. You have 2 by 2. This is, think that it's an ODE now. My space variable is Z, and it's just a radial variable. So this is a coupled system of 2 ODEs, and you're asking what do solution to this look like? So it doesn't look that friendly, but actually, so Göderli in 1941 gave us the answer to this question. Beautiful, beautiful computation. So Göderli, 1941. So the observation is the following thing. You know, if Z is my space variable, I don't like this term because I have Z dz term. It's non-autonomous. Okay, what Göderli tells you is that you can transform this non-autonomous thing into an autonomous system. Okay, so you can change variable. Let me ignore what the change of variables are. There's no point. You can change variables so that your new space variable is going to be X, but it doesn't matter. And then rho and psi are traded in an explicit way for 2 functions omega and sigma. And then your ODE, so the stationary ODE, if you want, becomes exactly this. You have delta of omega sigma omega dx equals delta 1 and delta of omega sigma d sigma dx of omega sigma. Okay, exactly what you get. And what is delta? So delta of omega sigma, so it's exactly omega minus 1 square minus sigma square, and delta 1 and delta 2, they are, let me not write them down, they are explicit polynomials around the 3 of omega sigma. Okay, and these polynomials have parameters. So what are the parameters? There are 3 parameters. So one parameter is D.
You're not the same function, right?
No, they are not. I'm absolutely sorry. Absolutely. Delta 1 and delta 2 are 2 polynomials, explicit functions of omega. And these guys, they depend on three parameters. There are 3 parameters that enter the picture. So D is dimension. L, typically for NLS, is P4 over P minus 1. And R, which is 2 over 1 minus E. So this is dimension. This is the nonlinearity. This is the speed that I chose. Okay, and at this point, so this is God given to me. If you want, this is my equation, and this I can choose it whichever way I want. Okay, this is my 3 parameter. So what can you do with this thing? Of course, you can. Of course, there is a huge difference between this and this. That this is autonomous. So all I need to do to understand trajectories is draw a picture. Right. So all I need to draw is the phase portrait of this. And this is very nicely done, actually, already in the paper of Göderli. Let me just. So I prefer to think of it like this. So I'm going to put here. Let's try to do a nice picture. So actually, this is the first time I do it on the board. So this is sigma. This is omega. What do I need to know? I need to draw delta omega sigma is going to vanish. So something bad is going to happen here. This is the sonic line. So this is 1. So this is delta equals 2. It's the sonic line. And then I need to draw delta 1 equals 0 and delta 2 equals 0. So it looks like this. So this is delta 1 equals 0. Actually, I have another branch there. Delta 1 equals 0. And delta 2 is the guy that looks So there are several ways in which maybe I can draw this picture like this and like this. Okay, it's roughly the picture, but this is delta 2. Okay, so this is roughly what these things look like. And as a matter of fact, there are a bunch of points which are particularly relevant in this picture. So this is omega. So here you have P4, which is 0, 0. This is what we call P2. Actually, these are Gödel's notation, maybe modified, but this is exactly what we found in this paper. So this is P3. And there is someone here, which is P5. Okay, so this is completely true. I'm just drawing. I have the zeros of my polynomial, if you want. I'm just drawing the sets where my polynomial is. And you understand that with this picture, you just put the signs wherever they are. You just put your little arrows and you draw all the trajectories. You understand all the trajectories of this. So there are books written about this space portrait, and they have been used in particular to construct tons of weak solutions of the equation, but this is not what I am interested in. What am I interested in? It's very clear. What I want is my flow to leading order to be given by one of these solutions. Okay, so think of it. Remember the picture that I gave you initially, the picture of original variable, the picture of R. I told you what the solution wants to look like. It won't be at the end of the day, I'm going to have these functions 1 over R to the alpha, and I'm going to have these crazy oscillations inside. It's going to start oscillating, but it will stop oscillating. The oscillations will stop. Okay, so how a solution to this equation can describe this? If you want, this is the region, if you want, in this renormalized variable, this is z equals 0, and this is z of size 1. This is the inner layer where things oscillate like crazy. And what I want this inner layer to stop. I want these crazy oscillations to stop. Okay, so what I want is that at some point, this crazy oscillation become damped, which in fact, in this language means I want z to decay. I want z, if you want, I want my solution. So how do I call it? So I don't know, typically I want density, if you want. I want rho of z to 0 as z goes to plus infinity. Okay, so I'm looking for a solution to this stationary equation, which is smooth at the origin, because I want to be smooth, and which decays infinity because I want to get out of my singularity. Okay, so it's a very simple problem. So now the question is, where is this solution on this picture? So all you have to do is look at your change of variable, and this solution is exactly here. There is a unique, so z equals 0, that is the origin is here. There is a point at infinity here. So there is a unique trajectory that does exactly this, just by looking at the phase portrait. So if you want, this is z equals 0. So there is a unique curve that comes from infinity over there. And actually this curve, you can follow it, and it will want to enter this point here. This is a triple point. You know, there are two triple points, P2, P3. And P2, P3 are, of course, are triple points. So there are points where everything degenerates. I will come back to this picture. Okay, so this unique curve, which is in T1, this is my only candidate for smoothness at the origin. It arrives here. And then where do I want it to go? I want decay at infinity. I want to arrive here. Okay, so the question is, can I go from here to here? So if you look at the phase portrait, actually there are, and I will be more specific on this in a minute, there are tons of trajectories that do that. Okay, so having a trajectory that connects z equals 0 to infinity, in fact, there is only one term here, but there is not a unique way of reconnecting here. I will explain more specifically where it is going. What does it mean? It means that if you look at your phase portrait, this is fantastic. You're absolutely in business. You will normalize, you drop a term, and you realize that this equation has a non-trivial solution, and this non-trivial solution does exactly what you want. It connects regularity at the origin to decay at infinity. That's fantastic, and you do not even have to work. The proof is I look at the picture. Okay, so nothing can be. It's like a dream. Okay, so let's start. So if you have this, so this is really ignoring the red term. So now you can start asking yourself. So you start the dynamical analysis of the.
You're going to explain what happens at that triple point?
Absolutely. But I cannot do it first without motivating this, because this is a little bit more work. So I need to motivate what's happening there. Okay, so in principle, you can take any of this yellow curve and start the dynamical analysis. So it simply means that maybe rho star of z, c star of z is my dash curve. I'd like to call it a solid curve if you want. Even though it's a self-similar solution. And I linearize. For the moment, I ignore this red term. I linearize and I try to control my flow. Okay, and I know exactly what I have to do, because this is exactly the kind of problem that you see in singularity formation problem. What you really want to prove, what you really want to show, is that you want to construct initial data so that the full flow asymptotically, rho psi as a function of tau and z, is going to converge as tau goes to infinity. So at least to my profile, rho star, c star. And of course, it's a question. It's a question of norms, right? In some well-chosen topology. This convergence cannot be true everywhere, but this is the typical picture. What you want is that after renormalization, you want to see your solution form exactly asymptotically in time this picture. Okay, so it's very clear what you have to do. You have to linearize, and it's a system. So if you call x equals rho psi, okay. So maybe I should do it like this. So maybe you would do it like this. You will do rho psi equals rho star psi star plus correction. I don't know. I'm going to call it x. So x is the correction. So it's a function of tau and z. And the leading order evolution of my problem here is exactly given to me by something like d tau x plus some Hamiltonian or some linearized operator if you want x is equal to non-linear term x. Okay, this is the rough page. Okay, and now what you want is very clear. What you want is decay for the operator h. You want to understand. You want to understand. You want to understand. So this is a very interesting question. So of course, when you do singularity formation, you will be type 1, type 2. People at the end of the day, this is exactly what people arrive to. Typically, when you have type 2, its Hamiltonian tends to be time dependent as well, which creates other problems. So if you want, there is a whole zoology in the literature of way to address this kind of questions and going around proof of decay for this kind of operator. One way, which would be particularly relevant for what I'm going to do, is something that was observed by Schrodinger and Circular. This goes back to 2012, I think, on the semilinear wave equation. And what they observe is that one way to get decay in this kind of problem is to go back to an abstract argument, which is the following. What kind of operator will typically, so maybe I want to put H, the question of whether I'm positive or whether I'm negative. Let me say equal and put it first. It's going to be the thing. So if you have an operator H and you ask for yourself what you're looking for is when is it that an operator what you want, the question you're asking is when it is that my let me not call it H, let's call it L, like linear, because H is going to be the space. Okay, so I have a linear operator L, and I want to ask myself, when is it that this operator has a spectrum? Because typically what you're after in this picture, you're really after exponential decay. And so there is a very natural class of operator which have if your operator, so if you have an Hilbert space H, and if your operator happens to satisfy a condition of the type NXX, your Hilbert space say control the constant times the norm. This is a so-called maximal accretive operator. And if you actually, so maybe if my operator is enough, if you typically satisfy a condition like this, then it's automatic that you have exponential decay. Okay, and in fact, there is a more general class of operator. If you can realize your operator L as being L naught maximal accretive plus K perturbation, where K is a compact operator in your Hilbert space H, then what you will have, what you can show is that in this case, you will recover exponential decay modulo finitely many eigenvalues. And then this is the typical spectral structure. So this is exactly what Schrodinger and Schrödinger use. This is the typical picture. So in other words, what you need to look, you need to express your operator. You need to find a Hilbert space. In which case, the dominant part, if you want, the highest number of derivatives, the symbol of your operator, if you want, is going to give you coercivity, and you have to be able to treat the rest as the compact perturbation. And this is the case. Then it's a theorem that the only thing that can happen to you is that your operator will have a finite number of eigenvalues, possibly stable or unstable. And modulo these eigenvalues, you will recover an exponential decay. So, okay, so fine. So there is so of course, this picture means nothing. The key here is what is my Hilbert space? It all has to do with how do I choose H? How do I choose a Hilbert space? And let me make my point. The reason why we will appeal to this kind of really abstract operator theory is really because here the linearized operator looks slightly nasty, and moreover, we have absolutely no formula on this yellow curve. You don't have much information on what it actually really looks like. So it's very nice to have, showing this kind of thing is probably the simplest way to go through this kind of questions. Okay, so how am I going to do that? So what is the natural kind of Hilbert space that I can think of in my equation?
I'm a little confused about the signs you have there.
Did I put a minus or
Maybe they, yeah, you probably had it the other way. But
yeah, it's like I want to be negative. I'm sorry, you're absolutely right. I want to decay H needs to be negative. Absolutely.
No, is L self-adjoint?
I'm sorry? Do
you want L to be self-adjoint?
No, so precisely, it's not. And this machinery does not require self-adjustment. This is a fundamental point. And the operator, if you linearize this is certainly not going to be self-adjoint because it's a Weyl equation. It's a critical point. Parabolic problem tend to produce self-adjoint operators, and indeed, and in some sense, getting the spectral theory right is easier. Hyperbolic problem tend to produce non-self-adjoint operators, so this kind of statement is particularly useful. So, okay, so what do I need to do what kind of Hilbert space do I have in mind? Well, it's very clear. So, it's very natural. And again, this is really related in particular to what we did when we studied type 2 singularity formation. And this is also what Dynamical and Schrodinger did. In that case, you want to build your Hilbert space by taking derivative. So you want to do something very simple. You want to say, well, essentially, roughly speaking, the picture is that you want to integrate something like you want to take, I don't know, maybe K derivative in Z of density and something similar for velocity. Okay, so but now you think of it twice, and what happens is very clear. You remember, so did I erase my face portrait? Oh, that was a huge mistake, actually. Oh, it's here. So sorry, it's here. So write down the equation again. So delta z omega dx is delta 1, delta dx is delta 2. So now it's like this. So this is z equals 0. You can decide that this is z equal 1 and that this is z equal plus infinity. Okay. So if you look at your operator, what's going on here is very clear. You see, my ODE degenerates on the sonic line here. That is, at this point says z equal 1. You know, I'm losing control of my derivative. This is exactly what you should expect on the sonic line. So my linearized operator is going to have exactly the same kind of problem. That is, if I draw z, so this is z, this is z equals 0, and this is z equals 1. If you want something wants to degenerate here, something is there, right? So this is typically what we like to call the boundary of the line. Okay, so this is exactly, so something is degenerate here. So this problem of degeneracy is something that already occurred. If you don't need to have a quasi-linear problem to have this problem. This is already something that occurred in semi-linear setting. This is something that occurred in the works by Koenig and Merle on energy critical wave equations. And there is a way to cook up, if you want, positivity with this kind of operator. So I have a problem here. So the typical strategy is to say, well, I'm going to take norms that actually are going to vanish typically on the boundary of the light cone. Okay, so you integrate, you just integrate inside the cone. If you get decay inside the cone, this is already very good. So it's a typical, you have to guess to get a decent norm in this equation. So what happens is the following thing. You do your algebra and you realize something very unpleasant. So you need to take sufficiently many derivatives of the equation because you need positivity. Sometimes you need to beat scaling, right? This is exactly what you need to do. So you want k to be large enough. But then if you want k large enough, this number here, n, becomes a function of k and of r. What is r? R is my hidden parameter. You remember my phase portrait, it depends on d, l, and r. Okay? So this number, so if I want k large enough, this number is going to start depending on k and on r. My problem is that as a matter of fact, so where do I want? I want this number, I want to have a decent spectral theory. I want this guy to be actually strictly positive. Okay, but for this, I need k to be greater than some k star. And my problem is that r, the parameter r, where does it? The parameter r limits the regularity of my solution at P2. Because there is something I did not tell you, and this is exactly what Peter asked immediately, is that something very funny is going to happen at P2 here. It's written here. I'm losing control of my derivative. At this triple point, something happens. And in fact, what happens is that generically, I lose regularity. I cannot be as smooth as I want. In fact, the regularity that I have here is some other function, k star. When you start doing your algebra and you realize the following thing, to have a decent spectral theory, the number of derivatives that you need is exactly k star of r plus 1. Okay? In other words, if you give me any of this curve, and you try, at least in the way we try, to find a Hilbert space to get maximal accretivity, which is the decent functional setting in order to make sense of this operator, and recover decay, what you encounter is that generically the number of derivatives that you need is higher than the regularity of the profile itself. This is something that does not occur in semi-linear setting. There is something very quasi-linear here. It means that the solution, in some sense, carries its own regularity. So this is something extraordinarily frustrating because you should think that this regularity here, actually by playing on the parameter r, you can make the solution as regular as you want. You can make this k star of r as large as you want, but you can make it as large as you want. In order to recover a decent spectral theory, you still need one more derivative. We're missing exactly one derivative. So one way, So what we did is the following thing. So now we need to analyze, so what's going on exactly at P2? Okay, so this is not now. Let me put it this way. If I can fix this problem, if I can fix this problem, I'll explain how we do it. It means that I recover a decent spectral theory. It means that I recover exponential decay in the light cone. It means, and now this is the expertise that we develop. We know how to propagate estimates, and we know how to close non-linear estimates. Okay, and you understand that the structure of the equation, of course, this is for NLS, so you have some structure here of the equation, but because this is Euler and because this is a correction of the Laplacian, now you can do the same kind of manipulation to go from Navier-Stokes to Euler. Of course, this term is going to change dramatically. You have to be very careful, in particular in the way density enters the problem, but the overall picture, the global structure of the proof is similar. It's about controlling Euler and showing then that the red term is under control. Okay, so the only thing I need to understand now, so we need to understand this regularity problem. Regularity problem. Okay, so this is a pure ODE problem. I have a very nice ODE, delta d omega dx equals delta 1, so which is a function, this is a function of 1 sigma, delta d sigma dx. Of omega sigma. So of course, what you want to do is build the principal direction of U flow. So in fact, you have an eigenvalue. You have one guy like this, and you have one guy that goes inside. And the way you can understand, so what we did, so if you want a general feature, so what you can do is the following thing. Because you can instead of thinking of x, you can express omega as a function of sigma, so you can think of omega as being omega of sigma. And what you can see is the following thing. This is really this is elementary. What you can see is the following thing. So we can maybe renormalize a bit, and you can see. So I introduce a variable u. So I would say that omega is omega of u, and the idea is that when u is equal to 0, I am here, and when u is equal to 1, I am there. Okay, so I'm sorry, I forgot to say one thing absolutely fundamental. Let me just back up 1 second. I forgot to say something fundamental. I told you that there is always a yellow curve that does this on this picture. But of course, this picture, this red curve and this green curve, they move with a parameter. Okay, so they move with D, L, R. So in particular, what could very well happen is that this point here is not there, it's on the other side, which would mean that my yellow curve, instead of entering P2, it could enter P5. And then P5 is an endpoint of my dynamical system because delta does not vanish, but delta 1 and delta 2 do. So if I reach P5 first, I'm never going to go there. So I'm doomed. Okay, so what I need to do, the first thing I need to check, to check that this picture is right. So to check that this picture is right, I need to check that P5 is at the left of P2. Okay, so this is something you can compute. It means that you need R to be less than R star, which is D plus L over L plus square. This is the condition that this point is here. It's not here. If it's here, okay. But what is R? Remember, R is 2 divided by 1 minus E. And E was the law for me. I wanted E positive. So this needs to be strictly bigger than 2. Okay, so
are you going to make your solution come very close to that point and then go down, or actually go through that singular point?
It has to go through.
And so when you hit that singular point, is there some deterministic rule?
I'll come back to this in a minute. Okay, I'm just finishing here on my exponent.
Okay.
I just forget to say that this picture is correct if this point is here, not here. And what does it mean? It means that you need this. So what is the condition? It means that D plus L needs to be bigger than twice L plus square root of D. So this is D minus twice square root of D bigger than L, and L is 4 over 2 minus 1. You need to find a P so that this is true. But this vanishes at D equal 4. it's negative for d equal 3. So if I do this for d equal 4, d equal 3, this is not the picture. This point is not there. This point is here. My trajectory does not exist. Okay, but starting in dimension 5, there is room. You do the same thing for compressible fluid. The threshold is dimension 2. Dimension 2 doesn't work. Dimension 3 doesn't work. Okay, so this is the first hint of how you choose the parameter. What is the supercritical numerology? Supercritical numerology is I want this picture, and there are many others that you can actually do. Okay, so this is the first thing. So now let's say that we are there, and let's answer Peter's question, which is the relevant question. So I arrive, my yellow curve. So what happens here? So it's a degenerate point, right? So what does it mean? It means that all solutions do the following thing. So I express, my parameter is sigma, and what you have is the following thing. So you can say that omega of sigma is the sum of k going from 0 to bk of ck, maybe this is a function of u to the j, plus c u to the gamma, plus higher order. Okay, so what is this expansion? I'm expanding for you what the solution looks like here. Okay, and what's going on here? So what is big K? So big K is exactly 1 over the distance between R star and R. So R star is this number here. So what you should think is the following thing. So I'm going to study this in a regime where this thing is an epsilon. So this is 1 over epsilon. So what does it mean is that I'm studying this phase portrait in the limit when P5 is very, very close to a P2. Okay, this I here, I make it as small as possible because I start seeing things concentrate and I like it. Okay, so it means, so what does this representation mean? What I'm right, so what is gamma? Gamma is something that it's the integer part. So actually, I'm sorry, it's the other way around. So K is the integer part of this, and gamma is 1 over epsilon. Okay. So what does this mean? It means the following thing. This point is a degenerate point. It means that trajectories are allowed to cross here. It means that, in fact, I have a Cauchy problem here, and the Cauchy problem is indexed by this constant. Okay, so it means the following thing. So you give me R, it produces this number 1 over epsilon, it produces this number gamma. If it's not an integer, then any solution that passes through there has this asymptotic expansion at P2. So U equals 0 is P2. So all solution, this is universal. This data is dependent on the data. And dependence on the data is on this constant. You give me this constant, it computes the rest of the expansion. This is very easy. Okay, so this is the shooting problem at P2. Every solution is of this form. Okay, so what's going on here? What's going on is very clear. If C is non-zero, you can take K derivative, you'll be fine. The K plus 1 derivative is going to see the fact that this thing is not an integer. Okay, so it's going to be singular at U equals 0, no matter what you do. Okay, so no solution is better than CK, except one, the one for which C is equal to 0. Okay, so there is one C infinity solution. The shooting problem starting from P2 has one solution, which is completely smooth. If this term is not there, it's very clear that you have an expansion. It's a C infinity solution. So there is always one C infinity solution. So now here is the dream. What do I want? There is a unique curve for any value of R. There is a unique curve that comes from there. But there is a unique curve that passes C infinity here. So can I choose R in a clever way such that these two curves match? Okay, so the answer is yes. I'm looking at the time. The answer is yes. So if you want the answer, so there is a sequence. It means that there exists a sequence arcade going to R star, such that if you want the separatrix, so the yellow dashed line, it's infinity. And let me explain more carefully how we do some. So this is the quantization number. Okay, it's very clear that this has to be exceptional. It cannot be, it's some sort of a shooting problem. And this has to be discrete value. So this is the sequence. Once you have the sequence, it computes all the numbers, all the blob speed, all the asymptotic, all the functions that are given you is based on the asymptotics of this function. So now, what's the strategy to do something like this? So the strategy that we did is to say, well, so we want to work in a limit when this epsilon, so epsilon is r star minus r, is going to 0. Okay, so you should see that this number here is 1 over epsilon. Okay, so it's very clear. So omega is not, it's not floating, it's there. Omega is satisfying a first order, non-autonomous, non-linear OOD. Okay, so this term, this CK here, you can compute that. In principle, you can plug them in. You can decide. You can compute. This expansion. Your equation is something like this. It's b minus u omega prime minus omega equals non-linear omega. Something like this. So you plug in an expansion like this, and you discover that you have an induction relation between, so schematically, it's Ck equals k Ck minus 1 plus non-linear. This is very schematic. And of course, in your coefficients, you have to be careful. There are some epsilons, right? Because this whole thing depends on R, and you can track how it depends on epsilon. So what is the strategy? The strategy is very clear. What we claim is that we can compute. So what do you want with your solution? So let's just zoom here. Yeah, I have the time. So let's just zoom here. So this is, I never know where the red. So I have the red. This is my eye. This is the red. This is the red here. This is the green. And I have a trajectory that's coming from over there. This is the one that I like. Okay. And then what I want is to study. So I study all the solution such that this term is not there. So it's very clear. This constant here is the last term u to the 1 over epsilon is enormous. So let's mean it means that when you're here, you don't see it at all. It's ridiculous. But as soon as you will start seeing it, you will see only him. You see, because it's u to an enormous power. So as soon as it starts taking power, it completely drives the flow. Okay, and of course, if you know this number, I told you that you could compute the rest of the solution. What does it mean? Is that there is an elementary fixed point that tells you that if you control what's happening here, you control what's happening here. So in fact, you understand what the function does. Okay, so give me this. Give me that I understand this number as a function of epsilon. So what's the strategy? The strategy is very clear. So now I told you, you need, for this representation to hold, you need gamma not to be an integer. If gamma is an integer, actually, there's a log here. The C infinity solution disappears. Okay, so what you do is the following thing. You take your parameter epsilon, and you do it in such a way that you let 1 over epsilon vary between a large integer, m, and m plus 1. Okay, so here at the boundary, your C infinity solution has disappeared. So where is it? Why does it mean? It simply means that it's probably the flow, the trajectory is something very violent. It's very concentrated. It has completely disappeared. And then you start evolving. In fact, you find a region, you start evolving your parameter in this region. Okay, and then what you see is the following thing. So if you know how to estimate this number, what's going on is like at the beginning of the interval in this zone here, and at the end of the interval, you can compute what happens on the right. And what happens on the right is very clear. At the beginning of the interval, you will exit immediately, and on the other side, you will actually will exit like this. Exactly. Okay, so it's the typical. So it means that it's at the beginning of the interval you exit red. At the end of the interval, so this is here. and this is here. Okay, so when you deform, you know that here you exit red, and here and again it's because you compute exactly what's coming. But what happened on the other side of the interval, so during this evolution, what you can show is the following thing. You can show that all along this evolution, your solution always exits on the same side. So there is an issue of parity. You need this to be even or odd. That is either they all exit on the left or red, or they all exit green. So the C infinity solution, you take C equals 0, you let your parameter R move in this interval, and you realize that at the beginning of the interval, you're like this, and at the end of the interval, you also go down on this side, but you went down on the other side. So there has to be a value which intersected the guys which is sitting there, and which is a very nice guy. Okay, so it's just a continuity argument. There must be a value such that indeed there has to be an intersection. So I don't know if it's unique, I don't know, but I know it has to be there, and it has to be there in every integral. So I have 3 minutes to explain to you. So the key now is how do we compute this guy? And this is a little bit scary actually, because this is a 1 over epsilon. It means I need to do an expansion, I need to control this guy all the way to 1 over epsilon. So there are 2 things. The first thing is that there is a formal limit problem.
What kind of information do you need to know about this?
So I will tell you exactly in a second. So what you have is that there is a limit problem. The limit problem is typically an ODE like x psi prime minus psi is non-linear psi, maybe that's a square. In some sense, this means that the coefficient here as a function of epsilon can be directly related to the expansion of this guy as epsilon goes to 0. Okay, this is very easy. You can see how one goes from the other. So, you know, what should you expect when you compute the coefficient of an ODE like that? This is very clear. If CK is the kth coefficient, you should the picture is that you know, CK is going to be k times CK minus 1 plus non-linear terms, because there are tons of non-linear terms. Also, if the non-linear term is not there, that's the gamma function. Okay, this is exactly your factorial. This is exactly what you should expect. CK wants to be like gamma of k or something like this. This is the typical picture of the growth of the coefficient as a function of k. There's a non-linear term here. But, you know, if the non-linear term was CK squared, I would be in very serious trouble, right? But you know how it goes. If you expand 2 holomorphic functions and you ask me which is the coefficient, it's never CK squared, it's a convolution. Right? So this nonlinear term is the convolution of the term that I had before. The convolution of gamma function, if gamma becomes very large, it's an empty sum. It's something essentially the first and the last term are dominant. So this is exactly, so what I did mean is that the higher the k, this coefficient grow like crazy. I'm not trying to prove holomorphy at all. It's the other way around. I'm trying to prove that these coefficients become mad. And as a matter of fact, the nonlinear term gets weaker and weaker. So what you can say, you can compute CK asymptotically. There's a number, roughly speaking. You can compute asymptotically how CK is going to depend on K. And there's a number that is a series that can be computed explicitly. So it's a series that is.
You need Stirling? You need more than Stirling?
No. So you need to see exactly what the. No. It's just that what I mean is the following thing. If the nonlinear term was not there.
No, I understand that. I'm just asking how subtle you need the asymptotics.
No. So we did everything with Stirling. Stirling is not. It's all about all the estimates are about estimating convolutions involving gamma functions and getting uniform bounds in terms of the parameter. Okay, but the endpoint story is the following thing, that asymptotically, CK looks like a constant times gamma of k. You understand that this number S star, it's a series actually. It depends just on L and T. Okay, so what I claim is the following thing, is that, so this number, so this is for the limiting problem. Okay, so now, if you understand the limiting problem, you have a similar structure. You see, your linear group here is not going to be gamma of k. There are epsilon everywhere. When k gets large, it's a huge deformation. Okay, so it's not gamma of k. It's something you could think of gamma b of k. Something that will have, it's an epsilon, gamma epsilon of k. Something that will have large deformations as k goes down. But my claim what we claim is that CK, if you want CK and epsilon, to leading order, it's S star plus small o of epsilon times the same thing. Simply because the same cause produce the same effect, it's just the decoupling in the linear group and in the non-linear. Okay, so it means that you have a complete understanding of the size. This, you know what it is. You have a complete understanding of the size of this. So this is how you can run your fixed point argument here to construct your solution. So there remains one thing to know. I need to make sure that this number is non-zero. Actually, maybe if it's zero, actually, it just means that I need to go to the next term. But let's not think about it. I need to check that this number is non-zero. So this number is a function of the nonlinearity that I'm giving myself and dimension. And it's given to me by a series. So it's really CK is K, CK minus 1 plus blah, blah. And we prove that the corresponding series is convergent. We, in fact, prove that it's a holomorphic function of L. Okay, so what we want to make sure is that this number is non-zero. So there are ranges of L for which we gave this to a computer. Okay, so we check numerically that this number, which is defined as an explicit series, and we know that the series is convergent, we want to check that this number is non-zero. So now the point is the following: there are ranges of L for which we are very confident are numeric nicely converged. It's very nice. There are ranges of L where it's less clear. You know, when it becomes too small, we get nervous. So we say the following words. We say this is a holomorphic function of this parameter. Okay, so all we need to do, if we want to make sure that it's essentially never zero or that zeros are isolated, we just need to check that this function is not zero in a zone where we are very confident with our numerics. And this is what we do. Okay, so there are regime of parameters where we can check we're confident on the numerics. There are regions where we're not confident at all, so we check it further away. And because it's a holomorphic function of the parameter L, it certainly tells us that holomorphic functions, zeros are isolated. So actually, most of the time, this number is not going to be zero. Okay, and this is how we. So this is how, in the end, parameters are chosen. So thank you very much.
I have a funny. You had the spectral problem where you had a co-dimension compact operator that you threw away some. How do you know that what you're throwing away doesn't come and interfere you in this subtle analysis with making?
Here?
So when you do this abstract spectral argument, you have to keep away from certain modes.
Oh, yeah. So this is actually, so this is exactly, so you have a bunch of instabilities in it.
Okay.
And you have a finite number.
Yeah, and here you also got a finite number.
Yeah, this is exactly the point. There is a finite number of.
And I want to make sure you don't destroy what you created here.
Yeah, absolutely. So this means that you need to choose your data correctly. So there are several. So it means that if you give me any data, if you perturb it generically, it will excite one of these modes. It's going to run out of the picture.
Right, so you
have to fine-tune the data, and of course, it's a nonlinear problem. So there are several ways in the literature in which people like to do that. We're using something that Frank Merle did 30 years ago. It's a very simple observation that you can use Brouwer fixed point argument to deal with the problem like that. It's just.
All right, I believe you. So you handled it.
Yeah, so it's just it's just you shoot on every.
Yeah, you got enough parameters.
Exactly, and you shoot and you say the only reason why I can become large, it's because of these parameters, and then you have a finite dimensional problem and you're done.
Just to make sure that these are not parameters of the problem, these are parameters of the initial data.
Yeah. The parameters are
I understand that difference.
on the data. Yeah. It has
But when you start playing finite against finite, you run into trouble. You need manual.
But the initial data
is infinite. Yeah, I understand.
So then,
yeah, it would be surprising if you ran into trouble.
So do you not need to choose any parameters to make sure that the curve that you get doesn't finally land up in P5 and just end? You wanted the curve to go to P1.
Well, yeah.
So P4, sorry.
You're absolutely right. So when I'm here, I need to make sure that indeed my enemy, I don't like this guy. Trust me, we fought it hard. I don't like this guy.
Yeah.
There's a separatrix here. There's a guy that's going to P5. I want to make sure that I'm not going there. So as a matter of fact, it's all about, it's all about computing here. If I know this size, and we know it, then I can tell you exactly what the solution looks like. I can tell you exactly how long I can wait. And actually, what's going on is the following thing, and this is the next one question. You don't need to wait. I don't know how to compute this solution. This representation is not good to touch red. I don't know how to do that. It's good. All you need to do is move away from this guy. This is your enemy. So if you want, there is a security here. All you need to say is, here, everybody's very close. All you need to say is, well, I'm sufficiently, I'm one away from this guy. Once you're one away from this guy, the flow will tell you that you have to go back. So you have to show, this is what we saw, this is the exit thing, if you want. We have to show that when we move our parameter here, the C-infinity solution systematically wants to reach this region. And in fact, this will happen essentially for u less than 1/2, that is, this is equal 1. Actually, you're very far from the separatrix relation. Another way of saying this is that if you want to go there, your parameters has to be much further in the picture.
I see. Okay. Where do you get the quantized values of the parameters? Like, it seems like you're choosing parameters.
No. So when I evolve my parameters, on the left, all the curves, okay, I just draw this infinity solution. On the left, all the curves exit, say, red. On the right, I don't know what they do. All I know is that at the beginning of the interval, they exit red. At the end of the interval, so I'm sorry, it's the other way around. At the beginning, they exit green. At the end, they exit red.
Right. Okay.
But then I'm done because it's
but you have a range.
So there has to be, the one I'm shooting for.
And you have to capture the yellow.
Oh,
There's only
there's only one.
Yes.
I see. Oh,
or the few
I
of
see.
them that might catch the yellow.
There may be tons of them that actually do it. I don't know.
Right.
I'm not telling you this, but there is at least one.
Okay, I see now. Thank you.
I had a question.
Yeah.
So for 1D Euler, for compressible, in my mind, I see blow up because in one space dimension, there's nowhere for the characteristics to go. And in 3 dimensions, I see a sort of tension between the mechanisms for blow up, but on the other hand, we have so much room for the characteristics to spread out and not run into each other. So I was wondering if you could comment on how this relates to.
I think that there are 2 things here. First of all, this self-similar solution, I told you D is a parameter. You do D equal 1, it's a completely degenerate picture. You see immediately it's a different world. So all this starts at dimension 2. This is the first one. The second thing, you're absolutely right that there are ways to think about these problems in terms of characteristics, in terms of characteristic crossing, etc. It's in some sense, it's another possibility. It gives you some information you can use. You cannot use it. It depends on the problem. We did not use it at all. We thought of this problem completely like a quasi-linear wave equation, if you want, and we think of it from A to Z as a wave equation. And one thing that the nice thing with this is that at the end of the day, the structure of the proof is very robust. I can do that for NLS. I can do that. In some sense, there is a program here that is very, very general. Okay, but you are absolutely right that maybe we could rethink this in terms of tools that are more specific to this kind of problem, typically trying to understand it in terms of characteristic, etc. It certainly would be perfectly relevant. It is a fact that we do not use any of this.
One thing you can say is that if you look at these profiles and you look at the characteristics which are associated with build profiles, just simply by construction, all these characteristics, they go to one point. And they all focus at the same time. So this is not what you typically see with a shock formation where you have a characteristic crossing and you have something like a cut locus. Here, it's a concentration mechanism. All characteristics want to go to one point, and then on top of that, you also have an amplification factor that makes your solution blow up, not the gradient blow up, but the solution itself.
You could have that like with a transport equation where the velocity is the sine function, I guess. You would have Nothing, sorry, nothing.
Are there any other questions? No, it does not seem to be the case. So thank you, Pierre, for your wonderful lecture.